All right, so we're going to start Doppler effect. Let's see if we can get this moving. Okay, so this is a little GIF showing you an object that is sending out waves. So you can imagine it's maybe a ambulance or a siren or something that's got a sound wave going out from it. And you can see when it's standing still, the waves move out in all directions at the same speed. But if the object starts to move, so in this case it's moving to the left, and then it bounces back and moves right, you'll see here, when it moves to the left, in front of it here, the waves are compressed because it sends out one wave and then it moves closer to it. Whereas behind the object, the waves are stretched out because it sends out a wave and then moves away from it. So what happens is, in front of the moving object, the waves are compressed, and behind the moving object, the waves are stretched out. And this effect is known as the Doppler effect, and that's what we're going to be looking at now. This is another GIF which shows you the same thing, just does a little bit more. It doesn't go in both directions, but you can see this object's moving a bit faster. It's getting closer to the waves in front of it, and you can see the waves are nicely stretched out behind it. Now this effect means we can actually use this to do some quite amazing stuff with it. So in front of the object, the waves are compressed, and the pitch of the so if these were sound waves, the frequency of the waves in front that are observed, if you were an observer and you were standing here, you're going to be observing more waves. More of these waves are going to be hitting you per second than if you were standing here. If you were standing at the back, then fewer waves would be hitting you per second. The wavelength between the waves you can see here is longer than the wavelength in front. So if you're standing in front, if you're an observer and you're standing in front, you'll be experiencing or observing more waves per second than an observer who's standing at the back. Now, if these were sound waves, then the number of waves that hits you per second is the frequency, the pitch of the sound. So in other words, low pitch sound is low, high pitch sound is high. So if you're standing in front of an object, you would hear a higher pitch than the actual sound. So that's why if a racing car comes past you, this might sound a bit daft, but you've heard racing cars, you hear as it goes past you. The sound is high pitched as it's coming towards you. When it goes away, the sound is lower. Same with an ambulance siren or a fire engine siren. I don't know if I can do that, but you probably hear bee-ba, 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 bee-ba. As it goes past you, there's a definite drop in pitch. You must also notice that the frequency behind the object and in front of the object is uniform. Although it's compressed, it's the same compressed frequency in front, and it's the same compressed frequency at the back, because the object's moving with a constant velocity. Obviously, if the object was speeding up, the compression would increase and the spreading out would increase. Right, so that's the basics of the Doppler effect. There, the slide just shows you nicely with the thing standing still. Any observer behind here would hear a lower frequency, and any observer in front would experience a higher frequency. Now, I'm saying experience and hear because you can have different kind of waves, and this effect works with any wave. So if these are sound waves, it would be something you hear. If it was visual waves, light waves, it would be something that you see. You would see a higher pitch in front, and you would see a lower frequency behind. This shows it nicely with an ambulance moving towards two people. The person in front, you can see here's the waves. Here the wavelengths are compressed, and the person in front is going to hear an increased frequency. Let's say this ambulance emitted sound at 300 hertz. The person in front would hear a frequency higher than 300 hertz, 350, 400, whatever. The person behind would hear a lower frequency. Right, so movement of the source relative to the observer affects the perceived frequency. Obviously, if the observer was running towards the ambulance, the same thing would happen. So it's relative motion. The source doesn't have to be moving. If either of the observers were moving, they would have the same effect. Now, there is a video here which you can go and have a look at. I'm not exactly sure, I can't exactly remember what it was, but you can go and have a look at it, and it might illustrate the point a little bit better. Anyway, let's move on for now. Right, so there's the wave stretched out a little bit. Now, I'm going to leave it there. That's just for the introduction. There is a little introductory worksheet which you can go and try. and maybe try and watch that little video as well, and see if it clarifies it all. There's a little introductory worksheet. You can have a look at the stuff on the notes that we've got up on the page for you. And if you think you've got it, then try that little introductory worksheet. The introductory worksheet just tests this kind of qualitative understanding of the Doppler effect. But in the next video, we'll move on to more complicated stuff, and we'll start the calculations. Okay, hope that helps for now.